feasibility of dairy manure and food waste co-digestion at small, medium, and large farms.
Okay, thank you. And we have 15 minutes, so we're going to move pretty quick. So I want to start off first with kind of a base of the fact that it's important for people to know that we do have technology for anaerobic digester systems, as well as for the energy part of the system, right? For the biogas to energy. And that includes for electricity, renewable natural gas, et cetera, that exists at many, many scales down to very small scales. So I'm showing you what I would call for this analysis that we did a large scale AD system of dairy manure and food waste, because what we considered as our largest scale is something on the order of 2,000 lactating cow equivalents. And that's very similar to this system that's in Vermont, where this is existing. So this is, for those who don't know, this was a Vanguard Renewables project. It is taking in manure and food waste. I believe the amount of food waste, or what has it up here. So they're not quite at, or I'm sorry, they're taking in quite a bit of food waste. So in this case, they're a little over what I would call 50% or half, half manure, half food waste, which is what we considered in our analysis down below in the green. And you see that they're estimating, or they're producing around 450 cubic feet per minute of biogas. So CFM is often what is used to kind of relate the energy output of the system. For our analysis, we had, you see the ratio of manure to food waste was a little different, and so based on the food waste and the compositions we were looking at for our analysis, we had about 600 CFM of biogas, so a little more energy out. So the way that this system was able to work economically in Vermont is by selling the renewable natural gas. That's the way they're processing that biogas into to customers that are really what I would call a voluntary or a third-party customer. So for example, the neighboring college is Middlebury College. I know there's also kind of an agreement with the utility. So basically ways to have a premium on that energy that's not fossil-based, right? That is able to be done by an entity to kind of represent or to kind of help fund these projects that are reducing greenhouse gas emissions. So it's not like officially on or participating with some of the regulatory carbon markets, but more on the voluntary side. So what we're finding with like this size system is that the economics are very, very strong. It's very easy to have a very good NPV, net present value, and then also, benefit to cost ratio. And, this can be done even at low energy rates. So $10 per million BTU is what we modeled. And then the food waste tipping fees are not out of the realm of what is very easy to obtain. Okay, they can now see my presentation. So I will move on. So I want to show you next what is a very, very small scale system. So I'm kind of illustrating the technical feasibility here with this. So this is what we would call micro scale. This is even smaller than what we analyzed in our economic feasibility study that we did. But what I want to show you is that the technology, it does exist. So there are ways to make this, I mean, if you can make this economical, right? And there are a lot of considerations or factors that go into it. It is certainly possible to build. So this is a tofu plant or a manufacturing plant in Seattle, near Seattle. And this has an anaerobic digester of 5 tons per day of waste. It's producing about 15 cubic feet per minute of biogas, so a lot lower than the other slide. And they are upgrading it to RNG. They're using a PSA, which should be spelled out, but that's pressure swing adsorption technology. That is usually the technology that can work for upgrading biogas to remove CO2, basically for that vehicle grade, right, pipeline grade fuel. It's the technology that kind of makes sense at the smaller scale and is usually the most cost effective. And then digestate, utilized for fertilizer in their greenhouse there. So I guess I want to first kind of step back a little bit and talk about New York State, where we've had that's where I work. So at Cornell University. The focus of a lot of my work is on New York, as well as just the Northeast region and what those anaerobic digester systems or manure systems look like. So we've had a lot of growth in AD in New York in the recent years, and this illustrates that. I guess I want to point out, without having too much time to dive in to some of this, is that we actually went from, first of all, 1.1 trillion BTUs of energy generation with about 48,000 dairy cows participating in digesters or processing manure with digesters in 2016 to 2.5 trillion BTUs at least of operating systems. That is from about almost 90,000 dairy cows now processing their manure with digesters. And actually, we went from 13 megawatts of electric to now 4.6, and also 21 million therms of RNG. So switched to RNG with the biogas energy output instead of electricity. And of the ones producing electricity, those are only the ones that now take food waste with manure because of really largely California's program, but a lot of this is participating with. And it's not quite all the ones that are generating electricity, but it's most of them. So just to give you an idea of what's actually happening in New York right now. So what we looked at was really this schematic of a system that we wanted to analyze for the economic feasibility at different scales. And so I won't spend too much time, but we had food waste, different types of food waste. We did have cheese whey as a portion of the food waste. That's very common. Not high energy, right? A lot of volume there, water, but definitely a waste that is present. And then confectionery waste was part of these are kind of our higher strength. So fats, oils, and grease. Confectionery, usually you take those in at smaller amounts. And then finally, we used examples of bakery wash water or bakery waste and meat processing plant waste as well. And then manure from the barns, obviously. Complete mix anaerobic digester system was assumed. And then really we focused on the renewable natural gas opportunity for all scales. So to generate biomethane and actually use some to heat the digester with a boiler. That was included in the analysis. So that means there's a net energy that would go out as what could be sold to others. And then digestate, you see, would be managed like manure is in our farm systems, where we've got long-term manure storage, uncovered, usually can be covered, and then application to the fields at the right time of year. And so we did also consider that in the analysis, both from the cost to manage the volumes of food waste, for example, right, being taken in, and how to manage that on the farm. So additional storage, application costs, and then also the potential benefits of digestate as a fertilizer, which is what we just heard, can have a lot of value when it comes to that nitrogen that's needed to grow crops. The problem is there isn't very good markets to manage that, especially when it's obviously not helpful on the farm that's generating it. So that's really what we have to figure out. So what we use to do the economic feasibility is a tool that's been developed like internally at Cornell so far, and this is based in MATLAB, but it's a very good system level tool for anaerobic digesters that can take in multiple feedstocks, so manure and a variety of food waste, and it has really BMP type data to predict the gas output. So it's not like a very intricate anaerobic digester model. So just so people know that. And then from there, you can do a lot of obviously just decisions with how you want to handle the biogas. So having it generate electricity or renewable natural gas or just hot water, for example, and then study economic impacts of what you're selecting with the operation costs and the energy costs, as well as food waste, tipping fees, carbon credits, for example. And so this is really the structure we used. So I just want to highlight the results. I don't know how I'm doing on time, but What we looked at, we did actually start even smaller than the 300 cow here. So 150 lactating cow equivalent is really the smallest operation we started with analyzing. So what that means is you'd actually have potentially like 100 milk cows and some, or 120 maybe, and some replacement cows. And then what we found was this really wasn't economic. It was very, very challenging. So we assumed we looked at different levels of revenue. So the lowest was $10 per ton of a tip fee for food waste, and then $15 per million BTU of renewable natural gas. I guess I want to stress that the revenue here could be split up in a lot of different buckets. So you could actually have, carbon credit as part of this. Maybe it's built into here, but maybe it's separate. You could also have digestate, fertilizer value, but that actually was not put into this so that we could keep it kind of simple with these two revenue streams coming in. And so you see that even at the high $40 per ton of tip fee, $35 per million BTU of RNG, 150 lactating cow equivalents. Can you build a project for 3.5 million? That's the break even. Probably not, but you might be able to. I think it would be hard. So this is really what we would say is not practical. Here, 300 cows was where we started to see that we could achieve economic feasibility. Because if you look at the final set of columns there is for 50% food waste ratio with manure. So what that means is we're adding an equal amount of manure with food waste. That was where we were able to see some project values that we would expect could be economically feasible. So something that would be higher than like 3 million, for example. And so really this was where, that would still be a challenge to take in a substantial amount of food waste, but that is where you could achieve it even for sort of moderate revenue values. So I guess from here, we went to kind of a medium scale farm, which I would classify as about 1,000 lactating cow equivalents. Think of it as 750 milk cows and 600 heifers. This is actually very similar to Cornell's total herd on their farms, I guess they have two. So what we found here was that we could achieve economic feasibility with higher revenue values as long as we with even 25% food waste. So not, too high of a ratio of food waste. You could still make this work. Some of the reasons why, food waste is a benefit to take in is because you do get some value usually for accepting it, but also you get a lot more energy out. And so really, if you can sell that energy, that's where that economic value can really play in. And so I guess one of the things to kind of note with this analysis is that if we could get 55% of the revenue from the first three revenue sources that are possible, right? So food waste acceptance, greenhouse gas reduction, which is huge, both from the food waste side, the manure side, as well as things like synthetic fertilizer, right? Digestate fertilizer sales themselves. If we could do that, then actually the energy production could be something on the order of $2 per therm, which is about 15 cents per kilowatt hour. That's much more realistic for where our energy prices are today. So basically food waste management and acceptance rate is a tough thing to navigate. Food waste comes in all forms and formats, whatever, packaged, right? Unpackaged, big pieces, shells, all kinds of things. So really, there has to be consideration for how, for the right types of food waste that make sense for a digester, generally more liquid. Packaged is fine, but we have to unpackage and depackage and not have contaminants. And so really some of this, I would argue, probably should happen off farm, because having a farm manage this is a lot. And it's also more small scale, so the economics don't really make sense. I also want to point out that compost and digestate are really complementary, right? Because we've got compost being carbon rich, soil amendment more solid and digestate being nutrient rich and really a fertilizer and a liquid. So we do need to think about that complementary benefit and how we can maximize that. And then, so a few questions to leave you with. Should there be tip fees for food waste? How could they be more predictable? So that is kind of a volatile piece of the economics because you can't really lock in a tip fee for very long and it does change. So how can we kind of reduce that as far as the farm economics go, right? How can digestate really get a value because it just frankly doesn't, and that's a problem. We have farms that use their manure and they can maybe use a little more of the food waste nutrients, but then what about other farms that are doing synthetic fertilizer? Can't we figure out how to get them this digestate and actually get paid for that and have it be a value? So, and then how can food waste really be processed off farm? So like that's food waste, there's a separator involved. It's a big system. And there is interest now from like Casella and some of the waste management people. So we need to just kind of work towards that. So I guess I'd encourage you to look for some more of our information that we have on kind of like the actual energy values that are happening in the marketplaces today. So you can start to see like this is actually like what we found was certainly possible to fit into these like voluntary markets, for example, but it does take like value from all the different streams of the system. So thank you. And I'm going to end there.